Yes, but well, our today's speaker is Petr Pushkar. Well, today's talk is not in integrable systems and not in geometry of equations, but in differential topology, but it seems to be quite interesting. I kindly ask everyone, except for the speaker, to switch off microphones, and in 2 minutes, we begin. You can meanwhile share your screen, Peter.
Yeah, you should make me
Олег, Олег, позвольте Пете расшарить экран.
Должно быть возможно.
Петь.
Да, наверное.
Ага. Okay, so let us begin.
Okay.
I'm switching my microphone off.
Okay, so I will speak on the following classical situation. We have a closed manifold, say compact without boundary, and we will consider Morse function on it. It's a function with all non-degenerate critical points. And really, I will suppose that function is strong Morse. It means that all critical values are different. Really, it was the initial settings of Morse. And I just add that all Morse functions form an open and dense set in the space of all smooth functions. Okay. Morse idea was to study function looking at the real filtration by sublevel sets, MC. And really, he discovered that one sublevel changed to another sublevel by adding handles, but without saying that. Really, it was the time before cell complexes. Cell complexes were invented only in 1948, it seems to me. Yeah, and Morse result were the sequence of inequalities. So-called strong Morse inequalities. Here I wrote them, where MK is the number of index K critical points, and BK is Betti number of manifold. And immediately we can get the corollary weak Morse inequality, which are just MK greater or equal than BK. And it was done almost 100 years ago. Okay, then in 1948, so complex was invented by Whitehead, and one can explain Morse theory in terms of cell complexes, and really there is a construction. We can construct starting from Morse, strong Morse function, we can construct cell complex. But this construction is, in general, is non unique. In general, is non unique, but number of cells is unique and given by the function f. So the number of cells of dimension k is mk. And on the level of homologies, we get a cell complex which is homotopy equivalent to manifold M. And its homologies is exactly homologies of M. And we get criticity weak Morse inequality. Okay. Then one can mention that if we take another cell complex, so M complex, it can be constructed step by step. We glue some cells with respect to an order of critical values. And on each step, we take cell approximation to get a cell complex. And we can take another cell approximation, and resulting differential will be conjugate by upper triangular matrix A. So we have the following natural problem. We we have a complex of finite dimensional over field F. And we have a total order on basis. And we have an upper triangular differential. Upper triangular with respect to an order. So it is exactly inequality that J is strictly less than I. And D square, of course, is 0. And we have an action of upper triangular isomorphism on that space. And the problem is describe orbits. And the solution to this problem will give us invariance of strong Morse function. This algebraic problem was solved by Barannik. Here, phi complexes up to upper triangular groups. And an answer is easy, that any upper triangular differential D is equivalent to unique elementary differential, such that its matrix is such a matrix that in each row and in each column is at most one unit, and all others are zeros. So the corollary is that if we have a manifold M compact and strong Morse function F, strong Morse function, and we fix a field, so this structure depends on field F. Then all critical points will divided in disjoint single points and pairs. Each pair is a pair of two critical points of neighboring index of A of bigger critical level point is equal to index of b plus 1. And for example, if we take, say, I don't know, this function on a circle, it has 6 critical points. And they will be divided in the pairs, it's a pair, and that pair, and 2 single critical points. Okay. And so strong Morse function and a field F will give us the following combinatorial structure: a normal form of differential of corresponding differential in cell complex. And that result, it has many interesting applications. It was initially applied to a problem of Morse theory of a function on a cylinder, m times segment. Okay, and now I will continue. We mentioned, and really it was mentioned long time ago, that in fact we have the same space of all upper triangular differentials, but really we have an action of unitriangular group on it. It's natural. Unitriangular group is upper triangular group with unities on main diagonal. So we see that we can try to extract invariance of strong Morse function by trying to consider orbits of that group. Okay, and theorem describing that orbits is the following: that each orbit contains exactly one rook type matrix of differential. It's a matrix with such that in each row and in each column is at most one non-zero element.
This is called Rook type, yes?
Yes,
Thank you.
it's exactly the definition of Rook type matrix. So of course, this Rook type matrix depends on initially fixed field of coefficients F. We assume that F is rationals or ZP, really. Okay, so that's a theorem of the last year. This classificational result belongs to unitriangular homological algebra, and it based on unitriangular geometry of some spaces with action of unitriangular group. And main object in that study is the following. We consider a vector space over F endowed with the following structure, enhancement. Enhancement is the following. One can define it on the following way. We take a full flag in the space. We know V0, V1, V2, etc. And we fix in each quotient space, in each quotient line, we fix an element. And this element is non-zero. So the stabilizer of that enhancement is exactly unitriangular group, of course. And the first theorem which a lemma to prove that classificational result that in each orbit there is one Rook type differential. Lemma is the following, that consider a space of all matrices of the size PQ, non-square at all. One side is P, and second side is Q. And consider an left-right action of upper triangular groups on it. We multiply of on one side by one size upper unitriangular matrix and another side by another unitriangular matrix. And we claim that each orbit contains one unique Rook type matrix, such matrix that in each row and each column is at most one non-zero number. Say that matrix is Rook type matrix. Okay. It's easy to prove that lemma, and I mentioned that the product of all that non-zero elements in the final Rook type matrix is a natural, it seems to me, it's natural generalization of determinant, because if the matrix is squared and non-degenerate, then it's exactly determinant. But if not, then it's another quantity, and it's interesting. Okay. What should I add also? That this construction, it shows that initial Barannikov structure, Barannikov pairs of critical points is a generalization of Bruhat cells to the homological algebra. Bruhat cells is the following. It's a division of GLN into orbits of upper triangular group. Where A and B is upper triangular matrix. Then theorem, easy theorem, claims that each orbit contains one matrix of permutation type. Such matrix that in each row and each column there is exactly one unity and all others are zero. And our construction of Rook type matrices is a fibration of Bruhat cells and generalization of cells and okay. So I want to add also
you mean generalization to the case of non-square matrices, yes?
Yeah, yes, of course. First of all, it's a generalization to non-squared matrices, and also we have a fibration. We fiber each Bruhat cells cell on torus, say like that. And I want to add also the following theorem. So it's a theorem about one parametrical Morse theory. So we consider a generic family depending on one parameter. And we consider
family of what?
Of functions.
Of functions.
Functions on manifold M. M is supposed to be a compact without boundary. And F depends on a parameter. This function is supposed to be generic. It means that for all Q except finite number of Q's, this function is strong Morse, and that all singularities are generic. It means that Surf diagram. What is Surf diagram? Surf is a mathematician, and Surf diagram is a graph of all critical values. So we take Q direction and R direction, and for each Q we draw all critical values. And we get a curve which calls Surf diagram. It's a curve with simple transversal self-intersection. Suppose that we fix an orientation of all, say, critical point of really of the space of negative squares. Then we have our structure with pairs and the corresponding numbers lambda. To get that structure, we need to fix orientations. If we don't fix orientation, then we don't have numbers, we have numbers only up to sign.
Pete, I don't understand. What do you mean by an orientation of a critical point?
Yeah, I mean the orientation of the corresponding cell in cell complex. On the level of real orientation it is an orientation of a negative subspace of tangent space at critical point. At critical point, we have a subspace.
Yes.
And it, roughly speaking, it divided into positive part where squares are positive and negative part. And we need to fix an orientation of negative part at each point, at each critical point.
Mhm.
To have an orientation of cell, to have a complex, you know, without it, we really don't have a complex because the basis of complex is oriented self, orientation. So suppose that we fix all orientations somehow. We don't have preferred way to fix orientation. Then we have in each vertical line, we have a decomposition into pairs and single elements. Into pairs and single elements. And to each pair we assign a number. And that structure, it may change when we have a singularity of search diagram, either at self intersection or at cusp. And I will describe how it changed.
What is this lambda?
Lambda is a number as in the rook type matrix associated to the differential. Differential is equivalent up to conjugation by unitriangular matrix to unique rook type differential. And in the rook type differentials, we have some numbers, lambda, VA, many of them, many pairs in general, and many numbers, non-zero numbers. In Barannikov approach, all that number became one, but really they are not one. And I describe how this structure changes when Q is passing through a projection of critical point on cusp of search diagram. So it's possible that our singular value is the projection of cusp. Then the situation is easy. Then the corresponding number, lambda, is in fact +1 or -1. Okay, and also we have a projection of self-intersection. Then it may be so-called free passing when we have one pair and say another pair and one pair pass through another pair, and the number lambda does not change at all. You may assume that critical points are far away, one pair from another pair. But it's possible that that pairs in the Barannikov normal forms are switching. So we have such a pair before bifurcation, and after bifurcation we have the same division into pairs, really. But the numbers may change. Lambda 1 and lambda 2, it changes like that. Multiplying by -c. It's one interesting bifurcation, and second interesting bifurcation is that when we have switching in the so we have one pair and one number, and second pair, second number. Then one number is multiplying by c, second number is multiplying by, strangely, by 1 over c and minus. And the symmetric bifurcation with same rule, symmetric with respect to is drawn here. And also one interesting case is when pair cross single then it may be whatever lambda and here another number without any law. And simple corollary is the following generalization of the result of Akhmetyev, Repos, and one more. I don't remember the third name. So consider say cylinder n times I. Where n is a closed manifold, and consider a function such that it's a perturbation of the projection to I. So is a function depending on parameter Q such that its surf diagram is compact and containing in the rectangle. Then we orient somehow all the critical points. And in that situation, special situation, we don't have the interaction between single points and pairs because all critical points divided into pairs. So in each cast we have the sign +1 or -1 depending on the number of lambda near this cast, +1 or -1. Then theorem claims that total number of self-intersections plus total number of negative cusps equals to 0 modulo 2. Okay, and it seems to me that is it. That's it.
This is the main result, yes?
Yeah, it's the main corollary. There are another, what is really interesting, and for me it was interesting corollary. so we have a space C infinity of M. This space divided into chambers of strong Morse functions. Yeah. And I thought about it, and I was in some sense sure that each chamber have finite number of walls, something like that. I don't know. Finite number of walls, but in general, it's not the case really. There are chambers of with infinite number of walls. It's another corollary of that theory.
Petr, what is the topology in C infinity?
Oh, topology, say, you know, it's hard question, by the way. I guess Whitney topology.
Well, but these chambers are in the space C infinity of M. So to speak about walls, you need some topology, otherwise it makes no sense.
Yeah, we have a space C infinity of M, and we have how it goes. I don't remember really, and we have topology of convergence of all derivatives in that space. It's a vector space of infinite dimension.
Okay.
And the space divided into parts by a hyper surface of all non-strong Morse functions. And it's really hyper surface. So what is wall? Wall is, I don't know. I may define a wall as a closure of some simple hyper surface containing Morse function with having the same critical values. It's one description, one type of walls. And also there is another type of walls, is a function with one degenerate critical point of type one cube and other squares.
Just one cube and all.
And all other, yeah, and plus some constant. So I claim that there are chambers with infinitely many walls. I even don't understand how to draw them correctly.
Impossible.
Impossible, yeah.
Yeah. Okay.
I may add also one more remark, and it's really interesting remark. So we consider unitriangular geometry. So we have a space and action of unitriangular group. Okay, I want to claim that unitriangular geometry is a limit of any geometry. For example, we can consider orthogonal geometry and degenerate it to unitriangular geometry.
How?
I will try to explain. Consider wait a bit. Consider matrix, say probably Z matrix. 1, 2, 3, etc. That's a family of matrices, diagonal matrices, depending on a parameter epsilon. And consider
Pete, these 1, 2, 3 are powers or
powers. Yes,
powers.
yes, are powers. So it depends on one parameter, epsilon. One parameter. We take such a function and we conjugate orthogonal group by this function, by this matrix. It seems to me Z type.
Okay, clear.
And here. And we conjugate it. And I claim that in the limit we will have unitriangular group. Probably I should speak on the Lie algebras, small o.
You mean when epsilon
When
goes
epsilon goes to zero.
to 0 or to infinity?
To 0, yeah. To 0.
Yeah, I think Lie algebra, not.
Lie algebra, yeah, probably Lie algebra. So and we make we may do such stupid operation with any geometry, and in each case we will get upper triangular group
So you
or
mean
its subgroup.
in such a limit, ON goes to unitriangular algebra, yes?
I mean that we will have upper triangular matrices. Yeah.
Okay.
Yeah. So it's a limiting geometry of everything. So in some sense, Morse theory, what is absolutely non-trivial, that Morse theory, very special theory, is a limit of regular geometries.
Sorry, what is the claim about the space of function on this picture? And above this, in this picture, C infinity of M. What do you say about it?
I say that this space is divided in parts. Each part consists only of strong Morse function. Yeah, and I call this part chamber. And I claim that it's possible, really possible, that chamber has infinitely many walls.
Mhm.
Here we have only 5 walls,
Mhm.
but really it's infinitely many walls. And we measure these walls with that number lambda AB.
Mhm.
And I forget to say that clearly that is a joint work with Misha Tёмkin.
No, you did not forget.
Ah, really?
Yes. Okay.
Okay, so
Well, Petya, thanks a lot for such a clear exposition of rather complicated and interesting matters. Any questions, remarks? No question, no remark. Uh-huh.
I have a question about this chamber structure on C infinity. So suppose as I understand, you have this walls there of codimension 1, and then you have singularities of codimension 2, and so on.
yeah.
And suppose that we take a loop in the space C infinity that intersects only the walls only in points of codimension 1.
Okay.
And probably some of the loops may be contracted without intersection of higher codimension singularities, and maybe some are not. Do you know about this? So maybe there is some something like invariant of the loop that says that you cannot contract this loop in such a way.
Cannot contract.
Something
A
like
loop?
vector flow.
No, I don't know. I should think. Thank you, Marina.
Okay, more question. Next Wednesday with the talk of Volodya Sokolov about non-abelian equations, well, really matrix varied equations, as I understand, and it should be also quite interesting. So I wish everyone good week. Well, to be healthy, and let's meet in a week. Goodbye.